Welcome and hello. This is a video exercise in RIMS, and in this exercise, I'm going to be dealing with approximating nonlinearity. Basically, we're going to be creating a nonlinear program and solving it using RIMS, and we are going to be using a piecewise linear approximation of a nonlinear phenomenon, specifically in network flows. So I have the RIMS interface up right here. This is the IDE. I'm going to introduce this problem by bringing out a network model right here. It's a very simple network schematic here where we have 10 CFS inflow entering node 1 through I_1, and then through panels A and B, or pipes A and B, 10 CFS is conveyed to node 2, and then the outflow from node 2 is, again, the same 10 CFS represented by this decision variable O_2. Associated with the two pipes, A and B, we have some data over here to the right. So we have the friction factor, the length, and the diameter. All right, down below here, I have the equation for the head loss through the pipe. Now, each pipe will experience the same head loss. That's just how network flow works. We have the friction factor, length, diameter, velocity through the pipe, and then 2 times the gravitational acceleration constant. If we substitute in Q over A for the velocity, and then also d squared times pi divided by 4 for the area, then this over here is the equation we get. So we have the head loss as a function of flow rate, diameter, L, F, and G, basically all of the variables we have right here. If we go ahead and write out the head loss, including a subscript A and a subscript B, that would just basically represent the head loss and the parameters through pipes A and B. We're ready to plug in the variables, which is this slide right here. And then in the next slide, I have the actual calculated values. So we have the head loss through pipe A and B written out as a function of the flow rate through pipes A and B. In this equation, the units for flow rate is going to be CFS, and then the units for head loss is going to be in feet. So if I go ahead and calculate these two, if I plot them out for a range that's from 0 to 10 as a domain for CFS, this is the plot right here. Again, with the flow rate at 0, the head loss is 0, but as the flow rate increases, the head loss through pipe A and pipe B are also increasing. Now, we know that the sum of A and B will be 10 CFS, and we also know that the head loss across those two pipes will also be the same. So if we happen to trace out a horizontal line on this plot to the point where that horizontal line intersects these two curves, and then we trace that down to the horizontal axis, the flow rate axis, then the sum of those two pipes should equal 10. So right now I've kind of sketched it out such that pipe A appears to be contributing about 4.4 CFS, and pipe B seems to be contributing about 5.6 CFS for a head loss through each of the pipes at about 0.8. Of course, this is just a plot. I'm just kind of doing a ballpark estimation. So this is sort of what I can expect when running this program and actually solving it. What I have on the screen here are, like I said, my initial guesses. I know the sum of the flow is going to be 10 CFS. So I'm just approximating 4.4 and 5.6 CFS out of pipes A and B. And then the head loss is about 0.8 feet. Now, instead of using a continuous line like this, we need to somehow put it into a linear programming solver. So to do that, I plan to divide these 10 CFS for both pipes into 10 separate segments of 1 CFS each. So 0 to 1, 1 to 2, 2 to 3, and so on. The next slide here shows the flow rate 0 to 10 CFS, and then what the head loss is in each of these two pipes at each of that integer value for CFS 1 through 10. So this is really just a more discretized data set compared to the more continuous curves we're seeing in the plot here. So we're going to return to this table, and I'll show you how we're going to use this coming up in just a little bit. All right, before we do that, let's go ahead and get started by building our project in RIMS. Here's my RIMS. Over here is the Project Explorer. I'm going to go right-click, New Project. Okay. Here's the new project dialog box, General Project. Go ahead and click Next, and then type in or paste in the name of your project, and then uncheck this checkbox, and then type out or paste in the path to your project directory. Okay, so there's my project directory. I'm going to click Finish. I created my project right here. Next, what I'm going to do is create a launch file. So right click, run as, and then run configurations. This dialog box popped up. I'm going to click on the Russell/RIMS2 application icon down here on the bottom of this left panel, and then click on new, the new button. All right. At the top, I'm going to give it a name. So instead of new configuration, it'll be called E13, Approximating Non-Linearity, E13 for exercise 13. Then I need to provide some information. This main Russell file is a required path. It's going to be a relative path from the project directory. I'm going to put it in my run directory and just call it main.wresl. Okay. Below that, the next three files are DSS files. I'm going to put them in a DSS directory. We haven't created it yet, but we will in just a little bit. Right now, we just need to set up the paths to those files. So I'm going to say dv.dss, sv.dss, and then the init file will be init.dss. Part A, I'm just going to be generic and call this project, and then state and init. Okay. I only need one time period. I'm not going to have a state dynamics equation that carries over variables between time periods the way reservoir systems and this program was probably meant to be used. But what I'm going to be doing is just need one single solver. So I'm going to select the same time period that it starts at. The start end date and start date and end date will be the same. So there's that. Next, I'm going to come up to this configuration tab and then check the checkbox to enforce the Russell Plus interpreter. And then on the far right tab, the last thing I need to do is click on the common tab and then click on shared, click on browse, and then click on the project that you typed in, and then click OK. All right, click apply, and then click on close. And then if we expand our project, we now see the launch file, which is right here, and we can see the file extension .launch is right there. So now in my project directory, let me bring it over into view here. Here it is. I have the .project file and then the .launch file right here. We need to add some more files here, like the files that we specified in the configuration. This right here is what I plan to build. We have these two files already in place. Here's the project directory. So I want to go ahead and add these files. I also need an objectives file, .wresl. Okay, I think that's all I need. So let's go ahead and get started on building that. Here's the project directory once again. I'm going to go right click, new folder. Run is one of the folders we need. The other one is called DSS. DSS. Okay, let's go into the DSS directory first. I'm going to create 3 new DSS files. Here I'm going to select text document dv.dss, then delete the existing file extension, and then just say OK. All right, I can copy this by just holding down Control and then left drag and then F2 to rename sv.dss, and then one more time for that init file. That's why we put all 3 of these files in the DSS directory. They're all ready to go. This dv.dss, this is the file that WRIMS is going to be writing the decision variables to. So let's go ahead and just get that ready. Here's DSS view. I'm going to go File, Open. Here's my project directory. Here's the DSS directory, and then here's the dv.dss file. Currently, there's no paths, but after we run the simulation, we'll come back here, refresh, and then view our data. All right, so that's the DSS directory. Here's the run directory. I'm going to create my main.russell file here. So new, text document is fine. Main.wresl. Okay. And then I also want a system directory. So this is going to contain the Russell files that I'm going to include in my main.russell file system. Okay. Inside the system directory, we want 4 more Russell files. inflows.wresl. Okay. All right, so I've got those 4 files built, and they're just blank files right now, but we're going to open them up and populate them. So let's go ahead and get started with that. I'm going to go up a level and open up the main.russell file first. Okay, here's that main.russell file. I'm going to do Control-O and then click into System. Here are the other 4 files I want to populate. All right, let's go back to our PowerPoint here to show this is the system that we're going to be sketching out. Remember, we have an I_1, an A and a B, and then an O_2. So I_1 is going to be our state variable, our constant 10 CFS inflow, and then our decision variables will be A and B and O_2, as well as a bunch of other decision variables I'll tell you about in just a moment. Okay, so back to, this is the inflows file right here. svar_1, set it to a value of 10, so that's pretty straightforward. The next file over is the channels file. I could have called it pipes, but basically this is the file with the decision variables. At the very top, we have our decision variable for A and B in O_2. They're going to be non-negative. The kind is going to be flow. The units will be in CFS. And then down below, I have subdivided the flow in pipe A into 10 different subdivisions. So we have A01, A12, A23, and so on, all the way up to 10. So what these are going to be used for is they're going to have a minimum capacity of 0, hence the STD keyword for a continuous decision variable in Russell Plus. And I'm also going to I'm going to say it has a maximum value of 1. The maximum allowable flow in pipe A is 10, and now I'm subdividing that flow into 10 individual discretizations, we can call them. And I'll show you where I'm going with that in just a little bit. But basically, the first CFS will flow up and fill up this first decision variable. And then after that, the second decision variable, and then the third decision variable, and so on. The same thing is true down here with decision variables B01. The total flow through pipe B can also be 10, and I'm subdividing that into 10 individual decision variables. So for instance, one potential scenario would be 5 and 5, right? We could have 5 CFS flowing through pipe A and then 5 CFS flowing through pipe B. So what I expect to have happen if that's the case, then my values for decision variables A01 through A45 would all have a value of 1. And then the other A decision variables A56 through A910 would all have a value of 0. And then same thing with B. The first 5 would have a value of 1. The second 5 would have a value of 0. But it might not be an even 5-5 split between A and B. It could be 4 and 6, 6 and 4, 3 and 7, 7, 3, whatever. So we're going to see what happens with that a little bit later. All right, the next file over here is our constraints file. So let me just paste in what I have here. If I scroll to the top here, it starts with the continuity constraints at node 1 and node 2. That's pretty straightforward. What we have is the inflow at I1 equals the outflow A and B. And then at node 2, the inflow A and B is equal to the outflow O2. So that's all we're doing right here. The continuity within the channels, this is similar to what I just described. So A is going to equal the sum of each of the 10 parts that create A. A could be from 0 to 10, and then each of the 10 individual discretizations of that flow in pipe A can be 0 to 1. Same thing with the flow in pipe B down below, same thing. And then what I'm doing down here is I'm setting the max capacity of each of the channels, A and B, to a maximum of 1. Not A and B, but the individual discretizations to 1. So we have A01 is a maximum of 1, A12 is a maximum of 1, same thing all the way down through B910 has a maximum capacity of 1. Okay, before we get to the objectives file, I'll leave this right here. We're going to come back to it in just a moment. I want to return to this slide right here. So what we're doing here is as the flow rate increases from 0 to 10 CFS, we have increased head loss, of course, through pipe A and pipe B. Now, if you only had one CFS flow, then which pipe would it go through? And you can't split it up. It has to be one CFS flow. Would it go through pipe A or pipe B? And the answer is it would go through pipe B because that is the minimum cost. 0.025 is a smaller amount of head than 0.038. And if you had a second single CFS to add, which pipe should it go? Should it go through pipe B, so it's 2 to nothing, or should it go through pipe A, so it's 1 CFS each? And the answer is pipe A, because at this point, we're going to be comparing 0.038 to 0.101, and clearly 0.038 is less. So after that, if we had a third CFS, pipe B or pipe A, so would it be 2B, 1A, or 1B and 2A? We would compare the 0.101 and the 0.151 head loss, and 0.101 is less. Therefore, we would allocate that third CFS here to pipe B. Okay, so we're going to continue that process and just sketch it out right here in Excel. And what I'm doing in this column V is I'm assigning the value, which will be the objective function coefficient. And I arbitrarily set it at 100 to be the highest because we already determined from that previous exercise 0.025 is less than 0.038. This is the same table with the same numbers, except I've added this value column, which we're going to be using for our objective function coefficients. Okay, so again, let's go ahead and just set the next one down to a slightly smaller value. We'll just count down by 1, so 99. And then what's less between 0.101 and 0.151? It's going to be 0.101, so we'll say 98. Now we compare 0.228 with 0.151. 0.151 is less, so that's pretty obvious. Next, 0.228 versus 0.340, so that's going to be a 96. 0.450 versus 0.340, the less is 0.340, so that's 95. Clearly 0.405 is less, that's 94. All right, so if I continue that down, this is what the results look like. Basically, we're going to start at 100, that's the highest priority. That's where the first flow of CFS goes. And then 81 is the smallest number. That's the 20th and most expensive head loss in the system because 0.3776 is larger than all the other loss values in this table. So anyway, I just want to explain where these numbers are coming from before we enter our objective function value. So here's the objective function value. And then if I scroll to the top, B01, here's the value, and then here's the variable, all the way down to our most expensive flow, which invokes the most head loss, which is the 10th CFS that we add to pipe A9. So let's go ahead and finish things off here. The last file here is the main file. So let's save that. Let's go ahead and save all of our files. And I think we're ready to run. Let's go back to our RIMS now. Right here on the launch file, I'm going to go right click and then run as. Okay, I think that ran. Let's go ahead and see if we have any results. Here's our dv.dss file. I'm going to go view, refresh catalog. Boom, there are our results. I'm only going to select the path for A and B. Everything else will be zeros and ones, but A and B will be the sum of all the A parts and B parts. Open up the table. And boom, here we go. Our answer is 4 CFS through pipe A and 6 CFS through pipe B. Now, this may feel rather unsatisfying because it's an integer and it's not very precise. And remember from our initial just estimation looking at the plot, we got similar numbers, but not exact. I would actually argue that our initial guess right here is more accurate than the results from our first iteration, where the flow through pipe A is 4.4 and the pipe B is 5.6 CFS. But what we got was this slide right here. It shows 4 CFS through pipe A, 6 CFS through pipe B. And if you trace those lines up to the curves A and B and then over to the head loss, you can see that we're close to 0.8, but not exactly. So our initial estimation was close, but again, using a 1 CFS discretization was just not precise enough to get us a very close answer. But we know for sure, based on the difference in the head loss that we can just eyeball from the plot, that the actual number will be greater than 4 CFS in pipe A and less than 6 CFS in pipe B. So what I propose for a second iteration, which will be the last iteration for this exercise, is what we do is further discretize our domain. So we know that there's going to be more flow in pipe B than pipe A, right? So it's not going to be 5 and 5, but we know that pipe B will have less than 6, and we know that pipe A will have more than 4. So I propose that our second iteration uses a discretization that is 0.1 CFS, and that the total range of that search region is 1 CFS. Specifically, pipe A is going to search between 4 CFS and 5 CFS, and then pipe B is going to search between 5 CFS and 6 CFS. So what I'm going to do now is update the files to make that reflection. So instead of 1 right here, the inflow, we already know that pipe A is at least 4, pipe B is at least 5, and we want to know how much more pipe A is than 4 CFS, how much more pipe B is than 5 CFS. So I could effectively just change this decision variable to a 1 and know that we start with at least 4 CFS through pipe A, at least 5 CFS through pipe B. And now we want to know, is it 4.1? Is it 4.2? Is it 4.3? And pipe B, we want to know, is it 5.1? Is it 5.2? Is it 5.3? And so on. So let's go ahead and just make that update. I'm going to break out the inflow file here. So instead of a 10 right here, I'm just going to delete the 0. Now we only care about 1. The sum of A and B is now going to equal 1 because we know it's already 4 and 5 in pipes A and B. We're just interested in how that last 1 CFS is divided between the two pipes. Our next file over here is the channels. So I'm going to Control A, Control V, Control A, Shift Tab. And then the first three lines here is the same as before, A and B and O underscore 2. That's our three main decision variables. And then what I'm doing here for A and the B pipes is I'm just discretizing them into 10 parts again. But instead of 0 to 1, this is 4.0 to 4.1. I'm using a P here to represent a decimal place. The next decision variable is between 4.1 and 4.2, 4.2 and 4.3. So if the total flow now through pipe A is 1 CFS, then the maximum flow through each of these individual part A pipes is going to be 0.1 CFS. Same thing is true with pipe B. Each individual pipe B part is going to range from 5.0 to 5.1, 5.1 to 5.2, and the max capacity is going to be 0.1 CFS. All right, the next file over here is our constraints. So let me paste in what I have prepared and go to the top. The continuity at the nodes, that's still the same. The continuity at the channels, this is similar, but a little bit different. Now the flow in pipe A is again going to equal the sum of the parts, the 10 different part elements of pipe A, where the maximum of A is 1, and then the maximum of each of the individual pipe A elements is 0.1. Same thing with pipe B. And then down below here, the max capacity in pipe A and pipe B, what we changed is, of course, the label, and I've also updated the maximum value from 1 down to 0.1. Okay, so if I scroll down, there's the bottom of that file. The next file over is the objectives file. So this is what we had before. And I hate to break it to you, but we have to redo this analysis. So I'm just going to clear out everything we have here. Then I'm going to come back to Excel. And now this table has changed a little bit in the second iteration. Now the flow rate through pipe A ranges from 4 up to 5 at a 0.1 CFS discretization. And then through pipe B, it ranges from 5 up to 6 CFS with a 0.1 discretization. Now, the values that you're seeing right here in the head loss column, that's the head loss associated with that specific flow rate. So you can check out the equation. It's the same coefficient that we calculated earlier, 0.03776. And then for pipe B, 0.02529. And that's calculated all the way through. All right, so let's go ahead and get started. If we had 0.1 CFS to divide between pipe A, which already has 4 CFS, and pipe B, which already has 5 CFS, which one should it go to? So the lower the head is the answer. 4.1 would be 0.635, and 5.1 over in pipe B would be 0.658. So I put a 100 right here if I'm just using the same arbitrary values that I did for iteration 1. I already have that in there sort of as a reminder where to start. And then if I had another 0.1 CFS, which pipe should it be? 4.2 in pipe A or 5.1 in pipe B? So 0.658 and 0.666. The smaller number is 0.658 associated with 5.1 CFS in pipe B. So I'm going to type in a 99 right there. Okay, now we're comparing 0.666 and 0.684. 0.686 is less, so we're going to go with a 98 there. Now 0.684 versus 0.698. The smaller of the two is over here in pipe B. So I'm going to type in 97. Okay. All right. So once all of that is done, the table is going to look like this. I've just populated the V column in each of these pipes. Just wanted to point out that I had to extend to the 4 decimal places when comparing 4.5 and 5.5 CFS. So that was pretty exciting. And with these values, I can now populate the objective function for my second iteration. And that's what you're seeing right here. Again, the weights range from 100 down to 81, and that's associated with adding 0.1 CFS to each of the individual pipe segments. Let's see, here is the main file. Nothing's changed about that. I'm going to click Save All, and then let's go back to our WRIMS. Here it is. Right-click, Run As. That ran. Let's check out DSS View and see if we have any updated results. So refresh the catalog. I'm going to click on path for part A. Oops. Oh, you know what? I'm going to go ahead and delete all the paths because I'm getting a little confused with the iteration 1 data. Okay, so I'm going to run it again. Okay, that's done. And then back to DSS View, refresh catalog. Okay, real funny. View, refresh catalog. There it is. Here's the path A flow. Here's path B. Let's open up the table. And then it's showing zero point 0.5 and zero point 0.5. So how we interpret that is with 4 CFS already in pipe A, we're going to add zero point 0.5. And with 5 CFS in pipe B, we're going to add another 0.5. So the 4 and 5 CFS came from iteration 1. Move that off to the side. Now we're looking at how to divide that last 1 CFS, and it looks like 0.5 and 0.5. It's an equal split. We go back to our PowerPoint here. Okay, so that was the first iteration. Here's the second iteration, 4.5 and 5.5 traced up to curve for pipe A and pipe B, respectively, and then over horizontally to the horizontal axis for head loss. It looks like we're pretty darn close to zero point 0.8. Now we could calculate exactly what the head loss is and continue this process with a third and a fourth iteration if we wanted to get more precise with our actual numbers. So I'm not going to do that for this exercise, but I did want to demonstrate how we can use RIMS and a linear approximation of a curve to solve a problem in water resources that involves a non-linearity.